Hi, everyone. I'm Mr. Pinola, and you just heard me trying to make a phone call through speakerphone. And when I was making that phone call, I was sending energy in the form of waves. However, the waves that my cell phone was using were not mechanical waves, as we learned about all through chapter 17. Instead, these were a new type of wave called an electromagnetic, or as scientists like to abbreviate it, an EM wave. The first thing that we need to consider is what the book definition of an electromagnetic or EM wave is. And according to your textbook, electromagnetic waves are the following. They are transverse waves consisting or made up of changing electric and magnetic fields. Maybe now you can see why it's called an electromagnetic wave, because of the presence of electric and magnetic fields. But just looking at the book definition isn't really enough to give us a full sense of what an electromagnetic wave is. So let me show you an animation that might clear that up a little bit. The animation you're seeing now on your screen shows an electromagnetic wave. Now we can clearly tell that this is a transverse wave, and that's because the wave energy is traveling in one direction, and the individual particles in the wave, or if we look at the crests and troughs, they're going in a direction that's perpendicular to the energy of the wave. This is what a transverse wave looked like, just like our last unit. However, you'll notice something different. It almost seems that there are multiple parts to this wave. We have the red parts of the wave, which represent, according to the key on the bottom, the electric field, and then the blue parts of the wave, which according to the key represent the magnetic field. Notice if you look closely, and specifically if you look at the end of the wave, closer towards where the arrow is, that whenever the red part of the wave goes up, so whenever the electric field increases, the magnetic field decreases. And also, whenever the blue or magnetic field increases, the electric field, or the red part, decreases. This is really easy to see again if you focus on the very end of the wave. This is what we mean by a changing electric and magnetic field. Whenever the electric field grows, it causes the magnetic field to shrink, and vice versa. Whenever the magnetic field grows, it causes the electric field to shrink. And the interaction of these two fields, the electric and the magnetic field, create an electromagnetic wave, which is used to carry energy, just like all waves do. We can visualize this interaction between the electric and the magnetic fields with this balloon that you see here. Remember how the electric and the magnetic field were perpendicular to each other? Well, I'm going to show that on the balloon. Let's imagine that the balloon, the long way represents the electric field, and the vertical way represents the magnetic field. If I squeeze the sides of the electric field, it causes the magnetic field up and down to grow. But if I squeeze the sides of the magnetic field along the top and bottom, it causes the electric field on the sides to grow. So it's important that the electric and the magnetic field interact with each other, and an increase or decrease in one will cause an increase or decrease in the other, and that will send energy along the electromagnetic or EM wave. Now let's take a look at some of the key differences and similarities between electromagnetic and mechanical waves. I'm going to do this by drawing a Venn diagram, which will allow us to really clearly see those differences and similarities. On the left side of my Venn diagram, I'm going to write any information that is only about mechanical waves, or the type of waves that we learned about in chapter 17. On the right side, I'm going to write any information that is just related to electromagnetic waves, or EM waves that we're going to learn about in the upcoming chapter, chapter 18. And anything that's in the middle is going to apply to both mechanical or electromagnetic waves. Now, you might remember from chapter 17, when you learned about mechanical waves, that there are three types of mechanical waves. There are transverse waves, in which the medium moves perpendicular to the energy. There are longitudinal waves, in which the medium moves parallel to the energy. And there are surface waves. And surface waves are when the wave is traveling on the boundary between two media. So mechanical waves, they can be transverse, they can be longitudinal, or they can be surface in their type. But for electromagnetic waves, they're a little bit more specific. Remember from the animation you just saw, transverse waves are only, electromagnetic waves are only transverse in their variety. And that means that all electromagnetic waves will look something like this. A wave that has crests and troughs, and that we can easily find the wavelength and amplitude of. Now, that doesn't mean that there are no similarities between transverse and electromagnetic waves. One of the key similarities I mentioned earlier when I was making the cell phone call, and that's the fact that even though they may be different types, or perhaps electromagnetic are only transverse while mechanical can be a few different types, they both carry energy from one place to another. And so that was something we learned about mechanical waves, and it's still true of electromagnetic waves. So both of these types of waves transfer energy. But how do they do that? How do these kinds of waves transfer energy? Well, if you remember mechanical waves, we created the first mechanical wave in the last unit by dropping a marble into a container of water. And so when the marble struck the water, it created a vibration or a disturbance that carried energy through the medium. So mechanical waves are created by a vibration or disturbance in a medium. This is sort of like when we learned about sound in 17.4. If you were to bang a drum, you would be creating a vibration that would send the energy from the drum through the air in the room to a listener's ear. And that wave that carried the energy from the drum to the ear would be traveling through the medium of air. But an electromagnetic wave is not created by a disturbance in a medium. Instead, an electromagnetic wave is created by what we learned about before, by constantly changing electric and magnetic fields. That's the last key difference between these two types of waves, and that is that mechanical waves need a medium to travel. And so if you have a mechanical wave, you need a medium, meaning a solid, liquid, or a gas, or some kind of matter to allow the wave to travel. If there was no medium, the wave couldn't travel at all. But for electromagnetic waves, that's a bit different. Electromagnetic waves are different in mechanical waves in that they do not need a medium to travel. So if you have an electromagnetic wave, even if you don't have a medium, even if there's no solids, liquids, or gases, the electromagnetic wave can still travel. Which is crazy to think about, Usually we have air that the waves can travel through. But for an electromagnetic wave, it can even travel through an area that has no air whatsoever. Let's take a look at how that works. We just talked about the fact that electromagnetic waves do not need a medium to be able to travel, meaning they can travel through an area that has no air. By the way, an area that has no air, that's called a vacuum, or an evacuated chamber would be a region that has no air. I'm going to show you a video that has a cell phone that has been placed inside a jar. And the teacher in the video is going to take all of the air out of the jar. And I'd like you to have a watch and see what happens to the cell phone that's been left inside when a call is made and the cell phone is left on ring.
So Caitlin's phone is now in an evacuated. That's a chamber with no air. An evacuated chamber. We're going to call. Will the radio signal, will the cell phone signal travel through the vacuum and cause the phone to ring?
Yes.
Sure it will. Let's see. There it is. And of course the light from the phone travels through the vacuum and you can see it fine too, right? But listen. I don't hear anything. You?
Nope.
Well, let's see. Now, I shut this off, so taking the hose off, that's not going to do anything. They're still not letting the air in. So go ahead, end the call. And what we're going to do is give it a few seconds to reset. Call again. And this time, I'm going to let the air back in as soon as the call comes. What's that? Who? What? Is it ringing or is it going to voicemail? There it goes. Okay. It's ringing again. We're going to let the air back in. Until the phone's flapping around from there. You're not going to hear anything until the air quiets down. And?
Oh, that's cool.
There it is.
Can I stop this now?
As you hopefully just knew, any region that doesn't have any air in it is considered a vacuum. In fact, outer space is a humongous vacuum. So that means all the space between Earth and all the other planets is just filled with nothing. There's no medium there. So that means that even though there is no medium between Earth and all the other planets, electromagnetic waves can still travel. So my cell phone signal could realistically travel through outer space, even though there's no air. But sound, since it's a mechanical wave, would not be able to travel through outer space. I hope you learned something today about electromagnetic waves. You should remember that all electromagnetic waves are transverse, that they are created by constantly changing electric and magnetic fields, and that they can travel without needing a medium.